Hello everyone and welcome to another lesson. In today's lesson, we'll be talking about hypothesis testing for two-sample tests. And this is chapter 10. So in today's lesson, we'll be talking about how to use the hypothesis testing for comparing the difference between the means of two independent populations, the means of two related populations, the proportions of two independent populations, and finally, the variances of two independent populations by testing the ratio of the two variances. So accordingly, we have structured this lesson into 4 areas. The first area we will be looking at two-sample tests for population means when the two samples are independent. Then we'll be looking at related samples. The third section will look at population proportion. And finally, the fourth section will look at population variance.
So first we look at two-sample tests for population mean, when you have independent samples. So in this particular case, under this scenario, we have two cases. Now remember, we are talking about two samples, right? So we have two cases here. When your population standard deviation of the two samples are unknown and assumed equal. Let me repeat that again. When your population standard deviation of your two samples, sigma 1, sigma 2, are unknown and assumed equal. The next one is when sigma 1 and sigma 2 are unknown and not assumed equal. What do we do? Right? So the point estimate of interest we are talking about here is x1 bar minus x2 bar. In the previous lesson, when we were talking about hypothesizing for population mean, our point estimate was x bar because we had only one sample. Here, since we have two samples, we're talking about the difference between the sample means x1 bar and x2 bar. So in these two scenarios, we are going to use something called a pooled variance t-test. And we are going to use population sample standard deviation SP to estimate the population standard deviation which is not known. And in the other case, we're going to use S1 and S2 to estimate sigma 1 and sigma 2. Why are we using only one particular sample standard deviation to estimate sigma? Because sigma 1 and sigma 2 are assumed equal in this scenario. When they are not assumed to be equal, you use two sample standard deviations, S1 and S2, in which case you use the separate variance t-test. What does this now look like? Our hypothesis, H0, H1. Well, for the lower tail test, you would be looking at whether what you're looking at is H1. You would be looking at whether your population mean for your first sample is less than your population mean in the second sample, that is a lower tail test. You identify an upper tail test by looking at your H1 again, whether your population mean for your first sample is greater than your population mean for the second sample. A two-tail test is where you would look at whether your population mean for your first sample is not equal to the population mean of your second sample. How does this look visually? All things that you know, just that there's a difference in how you state the hypothesis because there are two samples for your lower tail test, for your upper tail test, and then for your two-tail test. So remember, we are using the t-test statistic. Why is that? Because in all these scenarios, we do not know the population standard deviation. So that is why we are using the t-test statistic. Just a reminder, guys, if there is a lag or if you can't hear me, please let me know through the chat. Right. So what are the two sections that we are looking at under this hypothesis test for mu1 minus mu2 with sigma 1 and sigma 2 unknown and assumed equal, right? This is the case that we are looking at. So there are a few assumptions in this case. Samples are randomly and independently drawn. Populations are normally distributed, or both sample sizes are at least 30, and population variances are unknown but assumed equal. So what is the test statistic for this particular case? What is the case we are looking at? Population standard deviations are unknown and assumed equal. This is the test statistic in this case. It's a t-stat and it's a very long equation. Again, this equation will be provided in the exam. It's just a matter of you knowing which equation to use. So if you're talking about hypothesis test for two samples and you're considering the population mean, and if you go through the problem, you understand, look, your population standard deviations are not known and it is assumed to be equal. This is the test statistic that you should look at. You have the difference between your sample means minus, you have the difference between your population means divided by this particular equation. What is SP? SP is the pooled variance. Why do we talk about a pooled variance? Because you assume in your population standard deviations are equal, right? So you consider sample standard deviations and you look at a pooled variance using S1 and S2 and you come up with one particular number for your variance and you use that in your test statistic over here. And the particular confidence interval, one thing I forgot to mention here, which is very important. Now we are using the t-test statistic. Up to now in one sample test, we talked about the degrees of freedom being the sample size minus 1. What is the degrees of freedom if you have one sample and if you're using the t-test statistic? It is degrees of freedom equals sample size minus 1. Now in this case, you have two samples. Therefore, the degrees of freedom when you're using this t statistic is the sample size of your first sample plus the sample size of your second sample minus 2, because you have two samples, right? That's something important to remember. So this is the confidence interval you have to consider for mu1 minus mu2. X1, that is simply the sample means, the difference between your sample means plus or minus your critical value given by your t alpha over 2 times this particular value over here is your confidence interval. Okay, let's look at an example. How do we solve a problem? So we are talking about pooled variance t-test. Why pooled variance? Because we are assuming our population standard deviation is equal, although it's unknown. So you're told you're a financial analyst for a brokerage firm and you're asked, is there a difference in dividend yield between stocks listed on the New York Stock Exchange and the Nasdaq? You collect the following data. So what is the question asking? Is there a difference in the dividend yield? Is there a difference in the dividend yield between stocks listed in this and these two particular stock exchanges? So you're given the number of stocks that you invested in NYSE and Nasdaq 21 and 25. You're told the sample means. And you're given the sample standard deviations. You assume both populations are approximately normal with equal variances. Now, okay, that's important information. That is how you determine, look, there are two samples. Okay, so we are doing a hypothesis test for two samples. And they are asking for the question, is there a difference in mean yield? So we are talking about the population parameter of mean. Two samples, population parameter mean, equal variances. So we are going to use the pooled variance t-test. That's how this is what you should go through your mind when you're looking at the question. So how do you do this? So first, as usual, write down the H0 and H1. Now, how do we figure out this is how you write the H0 and H1? How do you know it's a two-tailed test? Because in the question, it asks, is there a difference in this dividend yield between stocks listed in these two, right? So they're asking whether there's a difference between these dividend yields. So that means whether it's the same or whether there's a difference. That's the implication given here. Is there a difference between the dividend yield, or is the dividend yield the same? So that is how you determine your H0 and H1. H1 says, look, the mean dividend yields are different. H0 is saying the mean dividend yields are the same. So you write those two down. When you write those two down, you know, okay, we're looking at a two-tailed test. So the test statistic, based on our numbers, you figure out what the equation is. You have to identify the correct equation and substitute in the correct values. So in this case, X1 bar, I'm choosing the first sample statistic as NYSE, and then the second sample statistic as NASDAQ. So you compute the sample mean differences and you compute the population mean differences, right? So in this case, mu1 minus mu2 is considered as 0 because why? You look at your null hypothesis and you find the value as 0. You note this particular value down, right? Because that is what you're either rejecting or not rejecting. So that is the value note down here, because there's no other value to figure out because mu1 and mu2 are not given in your example. So you look at a null hypothesis and you assume mu1 minus mu2 is equal to 0. So from this, you calculate your t-stat, which is 2.04. Now, what is SP squared? Again, you have to find out from the equations that are given. SP squared is this particular equation, a long equation here. N1 is the sample size of your first sample, which is 21. S1 squared is your sample variance. It's squared, so it's variance, sample variance, which is 1.3 squared because you're given the standard deviation. Similarly, you have your second sample size, standard sample variance, divided by N1 plus N1 minus 1 plus N2 minus 1. Guys, if you can mute the mics. All right. So from this, you calculate your t-stat. Now, what are you going to do with this? Well, similar to before, what we did, you write down H0, H1. You have your level of significance 0.05. Remember, it's a two-tailed test. Degrees of freedom. Now, this is where it changes. How do you calculate your degrees of freedom for a hypothesis test with two samples? It's the addition of the sample sizes minus 2, so you get 44. You compute your critical value based on your significance level and your degrees of freedom. You look at the T distribution table for T 0.025 because alpha divided by 2. Why? Because it's two-tailed test. You look at your alternative hypothesis and you determine it's a two-tailed test. Degrees of freedom 44. You determine your critical value for T. Now, sometimes in the exam, in the T table, you might not get 44. 44 might not be there in the table. So what do you do in this case? You just round it up. You look at the closest number that you have in the table, degrees of freedom. If it's 40, 40 is the closest number to 44. You write in the exam saying, look, 44 is not available, so I'm assuming degrees of freedom to be 40, and this is my critical value pertaining to the degrees of freedom of 40 and level of significance 0.025. So if you make that statement, the examiner can give you full marks because you identified that. Right, so you visualize it, you graph it, and then you calculated your test statistic here, which was 2.04. You identify where 2.04 is. It's somewhere over here, which is in the rejection region. What is the decision? You reject your H0 at 0.05 level of significance. What is your conclusion? There is a evidence of difference in means. So your final conclusion is, when you reject H0, when you are rejecting H0, your conclusion is there is evidence of difference in your means. That is your dividend yields. There's a difference in those dividend yields. That's what you're getting at here. So if you were to look at this from a confidence interval perspective for mu1 minus mu2, you would be asked, since we rejected H0, can we be 95% confident that the mean dividend yield of New York Stock Exchange is greater than the mean dividend yield you get by investing in the NASDAQ, right? So what is your confidence interval? You have the equation which is given in the exam. It would be the difference between the sample means plus or minus the critical value given by your t-test statistic times this particular value over here. So when you do that, you calculate your confidence interval between these two values, 0.009 and 1.471. Now, how do we answer the question, can we be 95% confident that mu NYSE is greater than mu NASDAQ? So how I've calculated it here is, I've calculated the difference. X1 bar is the sample mean you get, sample dividend yield mean you get by investing in NYSE. X2 bar is the sample mean for mu NASDAQ. So that is the difference I've calculated. That is, I've simply calculated X1 bar minus X2 bar is mu1 minus mu2. For mu1 minus mu2, I've calculated the sample mean difference. What is mu1? NYSE. Mu2 is for NASDAQ. When I calculate that, since 0 is actually less than this entire interval, right? This entire interval is greater than 0. You can say that we can be 95% confident that mu NYSE is greater than mu NASDAQ. Now, suppose 0 was in this interval, then you can't say this particular statement. You can say there's insufficient evidence. If 0 is in this interval, you can say there's insufficient evidence that mu NYSE is greater than mu NASDAQ. But since 0 is less than this entire interval, you can say we can be 95% confident that mu NYSE is greater than mu NASDAQ. So this is one example, and I will upload more questions pertaining to this particular area with another document, right? And I'll give you guidelines to answer, not the exact answer, but a guideline to the answer so that you can follow that. Right. So we were talking about hypothesis test for mu1 minus mu2, that is two sample means, difference between two samples means, when your population standard deviations are unknown and assumed to be equal. You also have the case where your population standard deviations are unknown and not assumed to be equal. That is the next scenario, right? So in that case, the test statistic that we are going to use is this. So what changes here is the denominator that changes, because in this case you're using sample variance of S1 and S2. You don't use a pooled variance. You use two different variants for the two different samples. Why is that? Because you're assuming that your population standard deviations are not equal. So how do you calculate the t-test statistic? This is how you calculate the t-test statistic. This is given by this. The degrees of freedom. Now, in the previous case, when you were assuming it was equal, in this case, it was very simple. Degrees of freedom was simply the sample size of your first sample plus the sample size of your second sample minus 2. But in this case, it's a little bit more complicated than that. It's given by this long equation, right? Which is variance of your first sample divided by the sample size plus variance of your second sample divided by sample size, whole thing squared. That is your numerator. Divided by, in your denominator, you have sample variance squared divided by sample size squared divided by sample size minus 1 plus sample variance of your second sample divided by sample size squared divided by sample size minus 1. So this is the equation for the degrees of freedom. That in itself is very complicated, right? So these equations will be given. You just need to identify for which case you're using this test statistic. You're using this test statistic along with this degrees of freedom for hypothesis test for two sample means when your population standard deviations are not equal. I've given an example here, right? But you don't have to worry too much about this particular section. Just know why it exists and what is there, what are the equations. Next up, so we've been talking about two sample tests for population means, talked about two sections. Population standard deviations are assumed equal and population standard deviations are assumed not equal. In both cases, population standard deviations were not known. So that's why we use the t distribution. Now this first section was for independent samples. Now we are going to look at two samples. What would happen to your test statistic and your whole scenario when your samples are related? So when your samples are related, let's first have a look at this video before I go into explain this. I'm going to play this video. Let me know if you can't hear the sound through the chat.
Let's talk a little about the paired difference t procedure. Pooled variance t, or Welch's t, which we've discussed previously, are appropriate when we have independent samples, but not when we have dependent samples. Consider this example: 4 students randomly selected from one of my stats courses, and what I've done is taken these 4 students and got their measurements on the first test and the second test. So the point of interest here, one important point to note, is that this is 2 measurements on the same student, and this is 2 measurements on the same student. So we cannot consider these samples from test 1 and test 2 to be independent samples, since we have these 2 measurements on the same person. Anytime there's 2 measurements on the same person or rock or car or what have you, that's kind of a dead giveaway that we don't have independent samples and that we shouldn't be analyzing things using a pooled variance t or a Welch's t. We do have other situations that are similar to this as well. So a study investigated differences in the volume of the right hippocampus, an area of the brain, in 15 pairs of identical twins, and one twin was affected by schizophrenia and the other was not. And here we have the results. This first pair is representing the volume of a slice of the right hippocampus for these 2 twins. This first twin did not have schizophrenia, this twin did. And so we have dependent measurements here. They're not the same individual, but there's certainly a tie in there. They're identical twins. So methods based on independent samples are not appropriate here. And to actually do the analysis, it's going to be pretty straightforward for us, though. We take the difference between the observations within each pair, and then simply treat those differences as a one-sample problem. And if we've been keeping up to pace and we know our one-sample problems, then this is going to be pretty easy. So my difference here is going to be 1.72 minus 1.55, and I'm going to get 0.17. That's my difference for that first pair. I do that for the second pair and the third pair all the way along, and I would also keep the sign. So let's do one where we get a negative difference. Here we get 1.09 minus 1.24, and so that's going to be minus 0.15. And we do that all the way along. And if we carried that out for all of those values, we would get what we see here. 15 differences. We've taken differences in all of those pairs, and I get my 15 differences. And once I get those 15 differences, I can sort of forget about all of this stuff here. I don't have to worry too much about these values. We've got our one sample of differences here now. We've got our 15 differences. N equals 15 differences. And we can carry out our usual one sample inference procedures on those. Those 15 differences had a mean of 0.15 and a standard deviation of 0.195, and I've plotted them out in a box plot here. And I've also drawn in a little line down here at 0, because 0 is an important quantity for us here because we're dealing with the difference between those values. And if your population mean difference is 0, then that's saying there's no difference between those groups on average, or there's no difference between the affected twin and the not affected twin on average in terms of the volume of their right hippocampus. So that's going to be a point of interest for us to investigate that. This box plot looks pretty clean, symmetric, and all the rest of it. There's one outlier up here. It's not overly extreme. It's a little bit out there, but it's not too extreme. If we plotted a normal quantile plot, it wouldn't look too bad. We'd still have that one little outlier, but overall it wouldn't look too bad. So I say let's go ahead with the one sample t procedures on this. And to do so, we need our standard error. And our standard error of x bar is just our regular old standard error from before, s over the square root of n. And this is simply going to be 0.195 over root 15, the number of differences that we have. Then this turns out to be 0.050. That is our standard error that we're going to use in our regular old one sample formulas. Now we want a confidence interval. Let's get a confidence interval for the population mean difference. And this formula should look very similar to things we've seen before. It's just our regular old one sample problem formula. We're going to need this t-value, and to do so we're going to need our degrees of freedom, and our degrees of freedom are just our regular old n minus 1, and that's 15 minus 1, or 14. So I go to a computer or a table, and I get my t-value in the usual way, and I can assume you know how to do that by now, so now we're just doing regular old stuff that we should be very comfortable with. X bar was 0.150 plus and minus. The computer tells me, or a table, that the appropriate t-value is 2.145. Multiply this by my standard error, and I get 0.150 plus and minus 0.11. And if I carry that subtraction out, an addition, I get 0.04 to 0.26. That is a 95% confidence interval for mu, the population mean difference, and I can be 95% confident that mu lies somewhere within that interval. And in the context of this problem, that means we can be 95% confident that the population mean difference for the not affected twin minus the affected twin lies between 0.04 and 0.16 centimeters cubed. We took our differences to be the not affected minus the affected in this situation. So the fact that this interval lies entirely to the right of 0 does tell us something. It looks like the twin not affected by schizophrenia has a larger volume of the right hippocampus on average. But we can carry out that line of thinking with a formal hypothesis test. If we want to test the null hypothesis that the population mean difference is 0, that is simply our null hypothesis that mu is equal to 0, and I'm going to choose a two-sided alternative hypothesis here because I don't have any real information one way or another. An expert in the field might think a one-sided one was more appropriate, but I'm choosing a two-sided alternative for us here, and then it's our regular old t procedure. X bar minus the hypothesized value, which is 0, over the standard error of x bar. We've run into this type of thing before. This is just 0.150 minus 0 over 0.050. And that gives us a t-value of 3.00. To get a p-value, we plot out our t-distribution. With 3.00 is out here somewhere. Our degrees of freedom is 14. We figured that out before. And so we want to get the p-value with this two-sided alternative. The area in the tail beyond this test statistic doubled. That tail area doubled because of that two-sided alternative hypothesis. And if we go to a computer or a table, we can see that our p-value is approximately 0.01. Our p-value is approximately 0.01. What does that tell us? Well, that's a fairly small p-value, and so that's giving pretty strong evidence against that null hypothesis. Or in other words, there's very strong evidence with a two-sided p-value of about 0.01 that the population mean difference mu is actually different from 0. What does that mean in the context of our problem, though? Let's go back and look at the data. Now recall that we were taking our differences to be the not affected twin minus the affected twin here. Not affected minus affected. And what we ended up with for our sample differences was an x bar of 0.150. And so the sample mean difference was 0.15 greater than 0. And this gives a strong indication that the twin unaffected by schizophrenia has a larger right hippocampus volume on average. One point to note, these pairs of twins were not a random sample from any larger population, and as such, any generalization to a larger population is a little bit suspect, but it's very, very difficult, say, and basically impossible to get a random sample of identical twins in which one has schizophrenia and one does not, and so sometimes we just have to deal with what we have, realize that there may possibly be some biases introduced, but we have to go with what we've got.
Right, that was a bit of a long introduction to this next section that we are going to look at, which is we're going to look at two sample tests, and these samples are actually related. So when you're given the question, it's very important now that you identify whether the samples are related or independent. If they are independent, we looked at two scenarios if the two samples are independent. If the samples are related, what are we going to do? That's the section that this particular section covers. So if you have related samples, first you must calculate the difference between the paired values, just like in the example in that particular video. You calculate the difference between the estimated values, and then once you calculate that, you calculate the average mu d. What is this? The point estimate for these paired differences are this, right? You calculate the point estimate, which is the population mean mu d for d. What is it given by? Simply add up all these paired differences and divide it by the sample size, right? And the sample standard deviation is given by SD by this particular equation. So what is important here? If you have a related sample, you're taking the differences. Now, as in the video, it's important which difference you take as well, because that will determine your decision or your conclusion as well. So here I've considered the first sample minus the second sample. Whatever decision that you come across will depend on how you define your difference. So that's important to understand. So again, the test statistic here is your t-test statistic. So throughout this lesson up to now, we've been talking about the t-test statistic. So that's interesting and that's easy to remember as well then. Just that the equation is different. If you have two related samples, your test statistic is given by this equation. What is d bar? D bar is the samples statistic for mu d, right? And you've calculated mu d and SD, based on which you can calculate your t statistic. What is the degrees of freedom here? In this case also, the degrees of freedom is sample size minus 1. So it's easy to remember. How does it look visually? Well, if you have a lower tail test, this is what it would look like. You have a level of significance. You reject H0 if your t stat is less than minus t. All of this, which is very similar. Only thing is how you write your H0 and H1. That's a little different over in this case, because your population parameter of interest is this mu d. What was mu d? You calculated the differences in your data points and you calculated the average, right? So this is your population parameter mu d. It can be either less than 0, then it's a lower tail test. If it's greater than 0, if you're testing for greater than 0, it's upper tail test. If you're testing for not equal 0, it's a two tail test. Again, remember, when you're writing your hypothesis, it's for the population parameter. You have to always keep that in mind. So next up, what is the confidence interval for mu d? It is given by this particular equation, your sample statistic plus or minus your critical value times your sample standard deviation SD divided by your square root in sample size. What is SD? It's given by this particular equation. All right, let's look at an example now. So you're told, assume you send your salespeople to a customer service training workshop. The question asks, has the training made a difference in the number of complaints? Has the training made a difference in the number of complaints? You collect the following data. So you have your different salespeople. You have your number of complaints before the training and after the training, right? Number of complaints. What's the first thing you do? Now, you first identify, okay, this problem is a related sample problem because you're taking the data points from the same customers, CB, TF, MH, RKMO, right? Before and after scenarios. So this is a related sample problem. You have two samples, hypothesis test for two samples where the samples are related. Okay, that's the first thing you have to identify. Then you know, okay, in this case, you have to first calculate the differences. So in this case, you can calculate the difference either way, but for this example, I've just calculated after minus before, right? After minus before, because the question asks, has the training made a difference, right, in the number of complaints? So I want to check whether after the training, whether the number of what has happened after the training to the complaints as opposed to before training. That's why I calculated the difference 2 minus 1. So I calculated the difference 4 minus 6 minus 2, 6 minus 20 minus 14, 2 minus 3 minus 1 likewise, and I added it up, all up, the total, which is minus 21. Then I calculated D bar, which is the average, right? So minus 21 divided by, you have number of people here, right? Which is, I think, 5. So you get 4.2. You calculate SD as well, right? Which is minus 2 minus 4.2 squared plus minus 14 minus 4.2 squared plus likewise, and you divide by 5 minus 1. Sample size is 5. 5 minus 1, you get SDS 5.67. This is the first thing you have to do. Right. Next, you write your hypothesis. Now, this is for a related sample, right? So you're testing whether the training has made a difference or not made a difference. So if the training has not made a difference, what was your population parameter here? Mu D. Mu D would not be equal to 0, right? So if mu D is not equal to 0, that means the training has actually not has made a difference. If mu D is equal to 0, the training has not made a difference, right? So we are testing at the level of 0.01, alpha points, level of signal 0.01, D bar minus 4.2. What do we do first? We calculate the critical values. So what is the critical value? We calculate the t-test statistic. Degrees of freedom is 4. The sample size was 5 minus 1 is 4. You calculate for, this is a two-tail test. So you calculate for 0.01 divided by 2. You get plus or minus 4.604. You visualize it. Alpha divided by 2, rejection region. That's your critical value. We move on to your test statistic. Very similar to what we've done now. The process is very similar, just that your notations and your concept is a little different. You calculate the t-stat, d bar minus mu d over sd over root n. You get minus 1.66. Where is minus 1.66? It's somewhere over here. So which means your decision is not to reject H0. What is the conclusion? You say there is insufficient evidence that there is significant change in the number of complaints. So if you don't reject H0, which means it kind of implies that you're accepting it, that means there's insufficient evidence that there is significant change. Why do I say that there is insufficient evidence that there is significant change? What was mu D? Mu D was after the training, the number of complaints minus before the training, the number of complaints, whatever population parameter. So we are saying we are not rejecting H0. It kind of implies that you're actually accepting the H0. So what is H0 saying? After and before training, the number of complaints has actually not changed because it's equal to 0, right? The average value. So that is why in your conclusion, you say there is insufficient evidence, there is significant change. Insufficient evidence, there is significant change in the number of complaints, right? I've given a couple of more examples here taken from the reference book. You can try this out. It would be quite similar to this particular problem. So now, up to now, we've been talking about two samples and we've been looking at the population means. We've been looking at the two samples being independent and being related. Now, next up, we're going to look at two samples for population proportions. Again, the process is very similar, just that the notations are different. So we'll have a quick look at this particular video again so that you understand, and then I'll go into the lesson. Just let me know if you can't hear this.
Let's look at an example of a confidence interval and a hypothesis test for the difference in population proportions. We'll use Z procedures that are based on the large sample normal approximation. A lot of research has gone into studying how homing pigeons are able to navigate to their home loft from an unfamiliar release point, but the precise mechanisms are still unknown. It is known that homing pigeons can detect the Earth's magnetic field, and that may be a contributing factor in their ability to navigate. A study investigated a possible effect of a magnetic pulse on the ability of homing pigeons to navigate back to the home loft. In the experiment, pigeons were randomly divided into a magnetic pulse group and a control group. Before being released, members of the magnetic pulse group received a strong magnetic pulse that was perpendicular to the Earth's magnetic field. The control group did not receive a magnetic pulse. The pigeons were then released from a location 106 kilometers from the home loft, and this was an unfamiliar release point for the pigeons. And it was thought that the magnetic pulse may very well negatively affect the pigeons' ability to navigate. 22 of the 38 untreated pigeons, the control group, navigated back to the home loft, and 21 of the 39 pigeons that received a magnetic pulse returned to the home loft. This was an experiment, but in a sense we can view these groups as samples from theoretical populations of homing pigeons that could have been released. We may wish to investigate a possible difference in the population proportions of birds that are able to navigate home. Does this data give evidence of an effect of the magnetic pulse? In experiments, people often take the difference as the treatment group minus the control group, so I'm going to call the magnetic pulse group Group 1 and the control group Group 2. But it doesn't really matter which group we call Group 1, as long as we remember which group is which. P1 hat, the sample proportion of magnetic pulse pigeons that return to the home loft, is 21/39, or about 0.538. P2 hat, the sample proportion of pigeons in the control group that returned home, is 22/38, or about 0.579. I often prefer to use more meaningful subscripts than 1 and 2, such as MP for the magnetic pulse group and C for the control group, but I'm going to leave them as 1 and 2 here so that it's consistent with the formulas we're going to use. The difference in sample proportions, P1 hat minus P2 hat, estimates the difference in population proportions, P1 minus P2. P1 is the population proportion for magnetic pulse pigeons. P1 is a parameter representing the true theoretical proportion of homing pigeons treated by a magnetic pulse that would return to the home loft under the conditions of this experiment. P2 is the population proportion for untreated or control group pigeons. P2 is a parameter representing the true theoretical proportion of untreated homing pigeons that would return to the home loft under the conditions of this experiment. In situations like this, we often want to estimate the difference in population proportions, P1 minus P2. So in this video, we are going to construct a confidence interval for P1 minus P2. And we are also going to test the null hypothesis that the population proportions are equal. This would mean that the magnetic pulse had no effect on the proportion of pigeons that returned to the home loft, under the conditions of this experiment. If we can reject that null hypothesis, that would mean there is strong evidence that the magnetic pulse did have an effect, and that might be a piece in the puzzle of how homing pigeons find their way home. First, let's construct a confidence interval for the difference in population proportions. Here's the formula. This is a large sample method, and it's not appropriate for very small sample sizes. In the example, the sample sizes were only 38 and 39. We'd prefer them to be a little larger, but overall the method is going to work reasonably well for this example. For the interval calculation, we take our best estimate of the difference in population proportions, which is the difference in sample proportions, and we add and subtract the appropriate margin of error. The margin of error is made up of the usual z sub alpha over 2 value, which we've discussed many times previously, times the standard error of the difference in sample proportions. As is often the case in statistics, the standard error can be a bit of a hassle to calculate. But once we have that, the calculations are pretty simple. So let's first calculate the standard error. Here are the sample proportions and the formula for the standard error. If we substitute in the values of P1 hat, P2 hat, N1 and N2, we end up with a standard error of 0.1131. I'm displaying all of the values to 4 decimal places, but if you're doing the calculations by hand, you should carry many decimal places throughout the calculations. Even better, leave the sample proportions as fractions in the calculations. That way you don't need to worry about rounding error. Here again are the sample proportions and the standard error. Suppose we wish to construct a 95% confidence interval for the difference in population proportions, P1 minus P2. Here's the appropriate formula. The point estimate of P1 minus P2 is just P1 hat minus P2 hat, the difference in the sample proportions. For the margin of error, we know from our past work that the appropriate Z value for a 95% confidence interval is 1.96, and we just calculated the standard error to be 0.1131. The difference in the sample proportions is minus 0.0405, and the 95% margin of error is 0.2216. If we carry out the addition and subtraction, we get the 95% confidence interval of minus 0.262 to 0.181. We can be 95% confident that the difference in population proportions P1 minus P2 lies somewhere in this interval. But what does that mean in the context of the study? It means that we can be 95% confident that the difference in the true, theoretical proportion of pigeons that would return to the home loft for the magnetic pulse group minus the control group lies between minus 0.262 and 0.181. One important point to note here is that 0 is contained within this interval. Based on the interval, 0 is a plausible value of this difference in proportions, and it is therefore plausible that the true proportions are equal. So based on this interval, this experiment does not give any evidence of an effect of the magnetic pulse. But if that's our point of interest, seeing if there is evidence of an effect, we can carry out a more formal hypothesis test. Let's test the null hypothesis that the population proportions are equal. This null hypothesis would mean that the magnetic pulse does not have an effect on the theoretical proportion of pigeons that would return to the home loft. What is the appropriate alternative hypothesis? That's debatable here. Because of the nature of the problem, we might think that the magnetic pulse would negatively impact a pigeon's ability to navigate. So one could make a pretty strong argument for the one-sided alternative hypothesis that P1 is less than P2. But I would suggest that the researchers would be interested in a difference in either direction, and who knows what the effect of the magnetic pulse might be. So I would err on the side of caution and choose the two-sided alternative. But opinions may differ on this matter. We're going to carry out a large sample Z test based on the normal approximation. And here's the appropriate Z test statistic. We take the difference in the sample proportions and we divide by the standard error. I use a subscript of 0 in this standard error because this standard error is a little different from the standard error we used in the confidence interval. Once we get the standard error, the calculations are going to be pretty simple. So let's calculate the standard error first. Here's the formula for the standard error. P hat is the pooled sample proportion, the proportion of all pigeons that returned home, pooling both groups together into one big group. Here are the sample proportions once again, and the pooled proportion is the total number of pigeons that returned home, which is 21 plus 22, over the total number of pigeons, which is 39 plus 38. This works out to 43 over 77, or to 4 decimal places, 0.5584. If we put these values into this standard error formula, as I did down here, we'd see that the standard error equals 0.1132. This is very close to the value of the standard error we used in the confidence interval, but it's slightly different. Now that we've got the standard error, the calculations are pretty simple. The Z statistic is the difference in the sample proportions divided by the standard error. Here that's P1 hat, which is 21 out of 39, minus P2 hat, which is 22 out of 38, divided by the appropriate standard error, which we just worked out to be 0.1132. And to 3 decimal places, this works out to minus 0.358. If the null hypothesis is true, and the population proportions are in fact equal, the Z statistic has approximately the standard normal distribution. So we're now going to get the p-value from the standard normal distribution. Here are the hypotheses, the observed value of the test statistic, and the standard normal distribution. The observed Z value of minus 0.358 falls right here on this distribution. Now that is not far out in the tails, so we can recognize right away that we don't have a lot of evidence against the null hypothesis. But we should quantify the strength of the evidence against the null hypothesis with a p-value. For this two-sided alternative hypothesis, the p-value is the probability under the null hypothesis of getting this value or something more extreme, something farther out in the tails. The p-value is double this area in the tail beyond the observed value of the test statistic, double the area to the left of minus 0.358 under the standard normal curve. If we go to software or a standard normal table, we can find that the area to the left of minus 0.358 is approximately 0.36. The resulting p-value is double that area, or about 0.72. That is a large p-value, which gives no evidence against the null hypothesis. If the null hypothesis were in fact true, the probability of getting the observed value of the test statistic, minus 0.358, or something more extreme, is 0.72, which is pretty large. So there is no evidence against the null hypothesis. There is no evidence that the true proportions differ. What does that mean in the context of this study? With such a large p-value, it means there is no evidence that the magnetic pulse had an effect on the proportion of pigeons that would navigate to the home loft. In short, we have no evidence that the magnetic pulse had an effect on the ability of the homing pigeons to navigate. Here are a couple of notes to finish. The sample sizes were not very large here.
Okay, that was a very long video on population proportions. So I think it covered most of the areas that I wanted to cover. We are testing for pi1 minus pi2, the population proportion difference. The point estimate that we are talking about is the sample proportion difference. And he also, in the video, they talked about this pooled estimate for the overall proportion is given by this particular equation. I also have an example here in this case, so we'll look at that as well. So the test statistic we're going to use now is different. You're using the Z statistic, a long equation again. The difference between your sample proportions minus the difference between your population proportions, your pooled population, pooled estimate for the overall population times 1 minus your pooled estimate for the overall population times this value, right? Your P bar, P1 and P2 are given by these values. How does this look like? Lower tail, upper tail and two tail tests. Well, in your lower tail test, you will be testing your alternative hypothesis where your population proportion of your first sample is less than your second sample. Upper tail, first sample proportion is greater, and two tail, the two population proportions are not equal. Visually, this is what it would look like. Up to now, we've been talking about two samples and we were testing for population mean. In both those scenarios we were using the t-test statistic. However, in this population proportions, we are using the z-test statistic. Knowing which test statistic to use is very important, and that is something that you can go wrong in the exam. So please make note of it. So one example is there a significant difference between the proportion of men and the proportion of women who will vote yes on some proposition? In a random sample, 36 out of 72 men, 35 out of 50 women indicated they would vote yes. You have to test at the 0.05 level of significance. What do we do? So what are they asking? They're asking whether there's a significant difference between the proportion of men and proportion of women. Proportion. So that means they're talking about population proportions example. There are two samples, men and women. So that means you're talking about hypothesis test for two sample tests for the population proportions. They're asking whether there's a significant difference between them. So that means it's a two-tailed test. Significant difference between these two-tailed tests. So what do we do? First and foremost, we write down the hypothesis test, which is given by this equation, because they are asking whether there's a significant difference between these two population proportions. Alternative hypothesis test says there is a significant difference. Null hypothesis would say no, the two proportions are equal. So this is what we're testing. Next, what do? We write down the sample proportions, P1 and P2. 36 out of 72, P1 is for men, P2 is for women. Note how I've written it down so that the reader understands what these P1 and P2 are. And then based on this P1 and P2, we write down the pooled estimate, which is simply x1 plus x2 over n1 plus n2. x1 is what? 36 men, x2 is 35 women, divided by this total n1 is 72, n2 is 50. So the pooled estimate is 0.582. We are just noting these things down because we identify the problem. We have the equations given. We are just now noting things down. Next, what do? We have to calculate the test statistic. Now, what is the test statistic in a population proportion with two sample tests? It's the Z test statistic. So we look through the equations given and we identify this particular equation, this one, right? And we substitute in the values. Remember, population proportion difference, we substitute in 0, the null hypothesis value, and we get minus 2.2 as the Z test statistic for the population proportion difference of pi1, pi2, minus pi2. The critical values for alpha equals 0.05. Critical value, remember, is a Z value here. In this case, it's a two-tailed test. So alpha divided by 2, so 0.025. You get the critical values as plus and minus 1.96 over here. So you get your rejection regions. Now where is your point minus 2.2? It's somewhere over here, which means it's in the rejection region. So what is your decision? Reject H0. What is your conclusion? There is evidence of a difference. So you reject H0 means there is evidence of a difference in the proportion who will vote yes between men and women. There is evidence of a difference in proportions because you reject your H0. What was H0? Mu1 minus pi1 minus pi2 was equal to 0. You reject that. Right. So your confidence interval is given by this particular equation. I've given a couple of more examples over here which you can try out. And if you have any questions, please do reach out to me. Right. The last section. So we've been talking about population means, independent samples, related samples. And then we talked about population proportion. The process is the same, just that the equations are different. You have to identify what the equations are. You have to identify whether it's a two-tailed test or a one-tailed test. You have to identify whether you're using a t-test statistic or a z-test statistics. These are critical things that you have to keep in mind and main areas that you might go wrong in. You have to keep those in mind. Finally, the last section, and then we'll wrap up today's lesson. Two sample tests for population variance. Now, up to now, we've not considered the population parameter of variance. In our previous chapters and in this chapter, we've been talking about the mean and proportions only. Now, here we are introducing a new population parameter, which is variance. So, when you have two samples, the two sample tests for population variance. We'll not watch this video, we'll go ahead. In this case, up to now, you only learnt about the Z-test statistic and the T-test statistic. In the T-test statistic, we had degrees of freedom. Now we are going to talk about a new test statistic, which is the F-test statistic, which is used for testing for the ratio of two population variances. That's what is important to keep in mind. We are testing for the ratio of two population variances. What do I mean? It will look something like this, right? So here, what we're actually testing is for the ratio. F stat is given by the ratio between the sample variance for the first sample divided by the sample variance of your second sample. And that is your F stat. These are your hypotheses, right? So this is a two-tail test. This would be a one-tail test. You're using the F statistic. That is what you have to remember. So that is your critical, that gives your critical value. How do you determine the degrees of freedom? The degrees of freedom in the F table as well is given by the degrees of freedom for your first sample, N1 minus 1, the degrees of freedom for your second sample, N2 minus 1, right? I've given the link for a F table over here, which you can check out. I've uploaded this lesson. What does it look like visually? Your F distribution would look something like this, somewhat skewed. Remember, this is not a normal distribution, so this is somewhat skewed. So this is in the left hand side you have your H1, which is sample variances are not equal. So this is kind of like a two-tail test. That is why you're considering your level of significance divided by 2, but it is only on one side that we are testing. Now, although this is a kind of like a two-tail test, when you look at your alternative hypothesis, remember you have to consider alpha divided by 2. But unlike in the previous sections, here in the F distribution, you're only looking at one area towards the right hand side. So this is a very important point that where students can go wrong, because in previous sections, of course, when you look at the alternative hypothesis, you draw the graph, you have on both sides. That's fine. You know, its level of significance is alpha divided by 2. But in this case, you look at the alternative hypothesis, I understand it's a two-tail, kind of like a two-tail test, but then you only look at one side of the graph. But still, you have to consider alpha divided by 2. When you look at the F table, this F statistic will give you the critical value. These are your rejection regions. And then if it's kind of like a one-tail, upper tail test kind of, then similar scenario, but you must consider level of significance as alpha. On the left hand side, it's like a two-tail test. You consider alpha divided by 2. Right hand side, you have to consider alpha. So let's look at an example before we wrap up. A professor in the accounting department of a business school would like to determine whether there is more variability in the final exam scores of students taking the introductory accounting course who are not majoring in accounting than for students taking the course who are majoring in accounting. Let me read that quickly. A professor in the accounting department of a business school would like to determine what does he want to see, what does he want to test, he or she, whether there is more variability. Okay, when you look at that word, you understand, okay, this is something to do with variance, but let's read on. In the final exam scores of students taking the introductory accounting course who are not majoring in accounting, that's one sample. Then, now we are going to talk about the second sample, for students taking the course who are majoring in accounting, not majoring in accounting and not majoring in accounting. Those are the two samples we are looking at. Random samples of 13 non-accounting majors and 10 accounting majors are selected from the professor's class roster in his large lecture, and the following results are computed based on the final exam scores, non-accounting and accounting. How many are there in the non-accounting? 13, accounting 10. So you understand there's a two-sample test that's sorted out. You're given the sample variances. Okay, we're talking about obviously we're talking about the hypothesis test for two samples where you're testing for population variances. At the 0.05 level of significance, is there evidence that there is more variability in the final exam scores? Now, this is how you identify your alternative hypothesis. Is there evidence that there is more variability in the final exam scores of students taking the introductory accounting course who are not majoring in accounting than for students taking the course who are majoring in accounting. Now, this is a long sentence which you have to identify, through which you have to identify, okay, what the heck is H1, right? That's what you have to identify. Is there evidence that there is more variability in the final exam scores of those who are not majoring in accounting than for those who are majoring in accounting? Assume that the population final exam scores are normally distributed. So this is the solution. Because here, like I underlined, it asks for whether there is more variability in these two, in this sample compared to this sample, not for majoring in accounting. That is how I've written it down, the H1. Not majoring accounting, population variance greater than those population variance in those who are majoring in accounting. I write down the H1, then only I write down H0. So if H1 is greater than H0, I know is less than or equal to. First, sort that out. That is so important to correctly identify your hypothesis. Very important. Next, it's very simple after that. You know you're going to use the F statistic. If it's talking about variances, two samples, variances, F statistic. Given by this equation, which will be given in the exam as well. So, in this case, you have to quickly write down what are the degrees of freedom for your first sample, N1 minus 1. First sample is 13 minus 1. 13 was those who are in the non-accounting one, and accounting is your second sample, 10. So 10 minus 1 is 9 degrees of freedom. Alpha is 0.05. So considering all of this, now what is the F value? Now remember, this is kind of like a one-tailed test when you look at the alternative hypothesis. So you have to look at the 0.05 value, right? Not if H1 was not equal to, if H1's over here said not equal to, then you have to consider F.025, where you divide alpha by 2. But in this case, this is like a one-tailed test, so you are considering this level of significance 0.05 as it is. The F value is 3.07, the critical value. Okay. Now, what is the decision rule? You reject H0 if your F test statistic is greater than the critical value. Now, how do you calculate your F test statistic? Sample variance of sample 1 divided by sample variance of sample 2. Sample variances are given, very simple in the question itself. Over here, it's given. You calculate it and you get 5.75. So we see that because your F test statistic is greater than your critical value, you reject H0 and you go on to the conclusion over here. So let's look at one more example just to get an understanding, the same example which we did before, asked in a different way. Is there a difference in the variances? Now I've directly asked the question variances, so it's very easy to understand. Okay, there are two samples. So we're talking about hypothesis test for two samples and testing for population variances. So we have to use the F statistics. So very simple. They're asking, is there a difference in the variances? So that means that H1 is, look, there is no difference. H0 is there is no difference, right? H1 is there is a difference. H0 is there is no difference. So you write down H1 and H0. You look at this. Okay, there is a difference, H1, and H0 is there is no difference. First, write that down clearly. You identify what your critical value is. Now see, you look at your H1, it's kind of like a two-tailed test. So you have to consider alpha divided by 2. So if your alpha is 0.05, 0.05 divided by 2, 0.025. This is for your numerator, the first sample, N1 minus 1, 21 minus 1. So my first sample in this case, I'm considering NYSE. Second sample is NASDAQ. That's what I've considered in this scenario. So I find out the critical value, look at the F table, 2.33, right? So in this case, the degrees of freedom, there's a degrees of freedom for your numerator and denominator. So then you continue on to calculating the test statistic, which is given by this equation. Sample variance of sample 1, sample variance of sample 2, 1.256. What was my first sample? It was NYSE, and second sample was NASDAQ. Now I compare this 1.256 with my critical value over here. So where is 1.256? It's somewhere over here, which means it is not in the rejection region. So F stat is not in the rejection region. So we do not reject H0. It is our decision. What is the conclusion? There is insufficient evidence of difference in variance at alpha equals 0.05. Right. So we covered a lot today. There are couple of more examples given here for the sample proportions example. You can go through that. I've also given what you can do on Excel, where you download and you use the analysis tool pack in Excel. How you add the analysis tool pack also I've given over here. By adding this analysis tool pack, you can calculate these values very easily, right? It's simply just selecting your data and just selecting what you require, and you'll be given the output like this. And this is for population proportions, but using the analysis tool pack, you can also calculate for all the other things that we've covered in these 2 lectures that we did today. So we did a lot today. First, we talked about hypothesis testing for one sample test. And then we talked about hypothesis test for 2 samples, under which we talked about population means when the samples are independent and when the samples are related. Talked about population proportions, where we use the Z-test. In these 2 cases, we use the t-test. For population variance, we use the F-test statistic, a new test statistic that we used. So, chapter summary. We compare 2 independent samples, compare 2 related samples, compare 2 population proportions, and perform the F-test for the ratio of 2 population variances. Again, the reference book that I've been using. So that's it. We will wrap up today. I didn't give a break because I want to finish this off. If you have any questions, please do reach out via email. I will upload more business application questions pertaining to these 2 lessons as well. Go through the document, the kind of tube document that I've already uploaded, and see whether you have any questions on that as well. Download the analysis tool pack for Excel and try it out. It's very simple. Yeah, so if you have any questions, please do reach out. I'll try and upload this recording on the Google Drive, but we'll see. Once your LMS is up to date, it's easier to upload there and for you all to watch through that. But I'll try and upload this video, this recording, to my Google Drive as well, and see whether you all can download it. Okay, that's it for today. Thank you very much. Hope you have a great day ahead. Thank you. Bye.